today what we're going to do, before we launch into wood with the NDS, we're going to take a little bit of a look at the load code, ASCE 7, which you may be familiar with from other classes, but we'll just take one day to kind of give it an overview. There is a lot in it, and we'll use it to some extent to, calculate the loadings for some of the problems. I was looking at it before class. This is the 2016. 2022 is apparently just coming out. There is this year it's getting a revision. It's like 300 and something, I wrote it down there, $310, wow. And pretty thick code. This is, just for interest, this was the code I originally started with. This is it, the ASCE 7, the 88 version. That's all. It was a much more digestible code. It didn't have quite all the detail of tsunamis and hurricanes, the different ice. Well, I guess it did have ice load in it though. But I don't know, it seemed to get you through. But now you got a little bit more to play with. Some of it, the reason it's expanded is they've taken tables that used to just be one table or something, or one chart, and they'd expand them into 3 or 4. Like for the wind load, they just used to have one wind load map, and then you'd add factors to get the correct importance factor or whatever. Now they have separate wind load for each of the importance categories. Why they bothered to do that, I don't know if that makes it more, maybe they changed it slightly, whatever. But so we'll go through, we'll take a little bit of a look at this. Probably won't get into seismic. We'll hopefully get through wind. If we can get that far, we'll be doing well. To begin, to start off, there is a classification of different risk factors on different buildings. So we put, when we determine the loads, it's, except for dead load is pretty accurately represents the actual weight of the structure. But the other loads are kind of your best estimate in a way, because you don't know that precisely, what the wind at your particular location is going to be, or how much, the 50-year worst snow maybe, but in some details, it's a little bit of a guess. So they give you a bigger safety factor on buildings that are more important, and then they cut the margin a little closer on buildings that aren't so important. So, and it's a kind of a, you could make buildings stronger and stronger, right? And just be certain it would never fall down under any load, but it would be unreasonable. Why would you would be wasting material, and it just is not the way it would make sense. So we determined certain buildings that are more critical, and they're ranked from 1 to 4. The least critical being, and here it actually lists them out in the commentary. It gives a much better description of what the building classes represent, and it's mainly based on usage. You can see in this chart, class 1 has maybe 1 or 2 or 3 people in it. Class 2 gets up to 100 and something. Class 3 is in the thousands. Class 4 is up to hundreds of thousands. So that would be the whole community, right? So you go from, different, and that would be the impact, the number of people that would be impacted if the building actually failed. So if you think of your garage, your barn, or whatever, okay, That's not maybe so critical if that were to fail. So it gets a pretty low factor. Category 2 is almost everything else that's not in the other 3 categories. So this would be residential, commercial, industrial, most buildings. Category 3 are buildings that house a lot of people. So movie theaters, somehow big lecture hall like our buildings across the street maybe. And then 4 are, look at that, okay, I was doing this last night. Apparently that one at the bottom, if it says 3 again, should be 4. 4 is ones that are particularly critical to maintaining safety during a disaster. So fire stations, police stations, hospitals, those kind of things. They also put into that category what they consider extremely hazardous material. So if it was a factory and it somehow failed, there'd be some sort of horrible gas or something released. That would be in that category. So that's the first step, and then that produces a factor that influences all the loads that we calculate. There are load combinations that we consider, and the combinations depend on our approach to design and analysis, whether we're using the LRFD, the strength design, or allowable stress. With wood, I mean, of course, the big advantage of LRFD is that it splits the safety factor, right? You have a gamma factor on the loads, and you have a C factor or whatever it is on the stresses. So you've got your safety factor more precisely tuned to the situation. So if you have a very high percentage of dead load, which you know very precisely, then you can lower the safety factor a little bit because you do know that load more precisely. So as a result, heavy structures benefit from this more. The first one to come out with it was concrete. Way back, even when I was a student, we were already using strength design concrete. And then steel came in several years later, a decade or 2 later. And wood, well, wood is a very lightweight material, really. So there's not a great deal of advantage in, I mean, the dead load represents a smaller portion of the total load. So there's not much advantage in using the LRFD. You don't benefit very much from it, if at all. So they, for a long time, there was no LRFD version, and then I guess maybe, I forget which code, a couple of codes ago, they added the possibility to calculate it with LRFD, and we'll look at that, but it's probably a little bit more straightforward. The code is really set up for ASD, so I think we'll go through, despite the fact that some of you may be much more used to LRFD, we'll do wood with ASD. It'll give you an opportunity to see what ASD is, how that works out, at any rate. And the difference it makes to the load combinations, you can see here in the LRFD you have these, whoops, I don't have my, you have the gamma factors, right, that are on there. And with ASD, they're not there. They're combination factors, but that's different. That's not really a safety factor. Okay. So, first one, dead loads. Those are the simplest, and they're in the ASCE 7 back. Well, this table's actually out of the commentary. They give you lots of tables of weights of materials. These are weights of actual construction materials, and they also give, and this is in PSF, like a, the weight of the surface or the floor. And then there's also just the base tables of the material weights. These are also, there's a table like this that traditionally was always available in the steel manual, still in there, I suppose. Or nowadays, honestly, you could just Google, some material and find out what it weighs. Manufacturers also provide specific weights. So, between these tables and whatever, you can usually find the weights of things. For wood, it's a little bit more complicated because with wood, we also have the matter of moisture content. And the moisture is a significant part of the weight of the wood. Like we talked about last time, in a fresh tree, in a living tree, it's like 200% moisture content. So there's a lot of the weight in the wood, in the water. So we do want to take that into account. The way we do it, we start with a density based on dry wood. So this would be like oven dry with no moisture. And we get a specific gravity, and the specific gravity for that dry wood is tabulated in the supplement of the NDS. And then you take that, multiply it by, to go from specific gravity to density, multiply it by the weight of water, and that gives you then the pounds per cubic foot, right? Weight. That would be the density. And then you could use that to calculate the weight of, if you know the volume of the wood, you multiply the volume, the density, here, to get PLF of a board, the density times the area divided by 144. I think we did this last time, in fact, in that first problem it comes up. So that would give you PLF if you wanted to get the total weight. I guess you could multiply it by the length. You could also just say that the volume times the density, right? And that would be the pounds, right, instead of just PLF. Okay. And so let's see. Oh, and the other thing with wood members is when they're in like joists in a line, we often like to get like the weight per square foot, right? And the square foot might be, I don't know, how can I represent it? Depends how big the square foot is, right, as to how many of these it catches. And to account for that, you have to average the joist out over a foot. So you take the weight of the joist, that would be the PLF of the joist, and then multiply it by 12 over the on-center spacing of the joist, and that would give you PSF for it. And I was thinking I might take I can get back over here. I was thinking I'd show you. Except I forgot to bring my calculator. I was going to show you how a problem works, at least this first problem. Maybe we could work through it together. And Okay, let me. Sorry, I'm coming in here. Let me show you what I'm doing. Whoop. That was a mistake. You could hit the other. Ha ha! Wow, this is almost impossible to control this mouse. Let's see if I can do it like this. Yes, I can. Okay, so here's the website. You go to problems. You go to login. Whoops, sorry, I don't want hers. or somebody else's problem here. I want mine. Yep. And then this. So this is your login, your ID number, right? It's real. I realize, you get typing that fast and your Kerberos password just automatically flows out of your fingers, but that's not what it needs. It needs your number. Okay, so let's try this first one. We could look, just for fun, at what we've got here. It's going to be given a floor system. We want to find the load on that beam, essentially. Okay, let's see if I can do this. Okay. You know what? This is not right. I'm so sorry. I pulled this up because it was already on my screen, but I think I got the wrong problem. Alright, let's try again. Okay. There. That looks like our first problem. Okay. Let's see. So, first thing is you probably want to you might want to even redraw this because it's very generic and it's kind of misleading in the proportions sometimes. I don't know that I'll actually withdraw it, but I'll. Oh, and I can't draw on this. Hang it. Well, maybe I will slightly redraw it. A is 17 and B is 11. Okay, so it's not too far off, right? This is 17, right? Is span A, and span B is 11. So this is 11 feet. Okay, so something like that. And then we have we're trying to find, oops, sorry, and this is a joist system, right, that goes across it, and we're given the on-center spacing of the joists, so these are 16 inches on center, and we've got a wood density, our density is 45 pounds per cubic foot. So that's given, we don't have to calculate that. The joist size is a 2x, these are 2x10s, and the beam that we're trying to get is a, wow, enormous 6x16. Okay, so, and the floor dead load, which is on it, is 3 PSF dead load. Okay, so we got that. the dead load of the floor joist. So that was what we were. If I can. All right. Let's see. Maybe I can do it like this. All right. The dead load of the floor joist. That would be in PLF, I think is what it was asking for, and that would be the density times the area over 144. So now, how do I get that other image back up? Huh? It's so crazy, I can't see my mouse. Oh, there it is. I've got to go. It's backwards from what is on the screen. It's so confusing. Okay, so let's see. This should be that. Alright, so we want to say the dead load of the floor joist was D times the area over 144. So the density we say is 45. The area of a 2 by 10 we can look up in our NDS real quick. This is on page 14. 2 by 10 gives me 1388. Over 144, and then I need one of you to help me, like this gentleman in the front row here with a calculator in his hand. Can you run these?
It's 4.33.
Okay, thank you. 4.3. Yeah, we did this last time, right?
Yeah.
Sorry. Okay, so now if I can type it in. Let's see. 4.33. Okay, so that works. Then we want the dead load of the floor joist again, but now in PSF. So to get that into PSF, we take the PLF, right? This load, the PLF times I think it was 12 over the on-center spacing. Right, so that would be 4.33, and it's 16 inches on center, so we're going to reduce it a little bit, right? Okay, so what's that come out to be? Can you get that?
3.2.
3.25, okay. So we get that guy. Okay, now, the total floor dead load. All right, well that's pretty simple. That would just be the this load, the load of the member, and we're looking for it in PSF. So the load of the member, 3.25 plus the applied dead load, which is up here, that one. So that would be 3 and 3 should be 6.25. We got that. Okay, so far so good. The floor live load. Now this one we have to look up. This is the occupancy, and this we didn't quite get into live loads yet. Let's see if I can do this. Probably the next slide. This is all dead load. And this goes into live load. And live load in the ASCE 7 gives you several charts and by occupancy. So you look at the occupancy, and then it'll give you the load. It'll give you a minimum concentrated load that might occur, but the main one that's important are these loads. And this one, it's in PSF first, and the brackets are kilonewtons per meter squared. So we want, what did I have? Assembly fixed. It's assembly with fixed seating, right? Okay, so assembly with fixed seats. There we go. That's that guy. So I should be looking at 60. So it's just a matter of pulling it out of the chart. And you should be able to go down that chart and definitely find, I mean, I think I gave everybody one that was definitely in the chart. So you shouldn't be lost. You just need to find it. Okay, so now, oh golly, now I gotta come back to this page. Okay, so that would be this one, and we said it was 60. Okay, man, we are on a roll. Self-weight of beam A. Self-weight. So the dead load of beam A. And beam A, we said, was 6 by 16. It's a real monster. 6 by 16 has an area of 8525. So the area of that guy is 8525. And if we want the dead load, it's still got the same density, so it's the same calculation as what we did before with the joist, right? We should say 45, the density is this calculation. 45 times, right, 8525 over 144. So we can knock that out for me. That's in PLF, right?
26.64.
What?
26.64.
Oh, and you know what? Actually, we didn't even have to calculate that. That's in this table. If you look at a 6 by 16 and go across, it'll show it for 45 pounds, 2664. Okay, good job. Okay, so you should get that one. For some reason, my answer came out a little rounded, a little round off there maybe. But that was correct. The total dead load on beam A. Okay, total dead load. So this is going to be from the floor, like we take a 1 foot strip here. Oops, I can't draw it. We take a 1 foot strip coming onto that floor, so that so we have a PLF from the joist coming onto it, right? And we already know, let's see, we already know some of this. We have the PSF of the total floor dead load PSF. That would be 625. So we want to take, I'm taking a 1 foot strip here, right? And finding the weight of it. So this would be the depth of it here is 5.5 feet, and the width is 1 foot wide, so the area is 5.5, and the weight in PSF we said was 6.25, right? So it's 5.5 square feet times 6.25 pounds per square foot. So that should give me the weight of that. The weight of that. Now, wait a minute, is that all? The total dead load on A. So I think that also includes the, this, wow. Not too well worded whether that actually includes beam A or not. I think it probably does. It says total. I should have added including the dead load or self weight. But okay, let me see if it does So what, first off, give me this.
34.37.
It's what?
34.37.
34.37. Okay. 34.37. And then if I add to that the dead load that I have here that I didn't write down, I guess. What was that? 2664. So 2664. So what's the total come out then? About 50, 60 something, huh? 60, 61, 60, yeah, almost exactly 61, huh?
61.01.
Zero. Okay. 60. Let's try this. Oh my goodness. Hope it's right. 61. Ah! Okay, yeah. Not the best way. I should have maybe worded that a little better that it included the dead weight, but it says total dead load. Okay. Now the total live load would simply be coming from the floor, and that we already calculated somewhere. The total floor live load in PSF is 60, so we just need to take that 60 now. So that this was dead load. For our live load, we need to take the 60 times this. Oops, not that one. That 5.5 feet. Sorry. What's that? 300 something?
230.
Huh?
330.
330. Okay. Alright. Last one. Okay. 330. Ah! Hooray! We nailed it. Look at that. 35 out of 35. Good job. Alright, so at least that takes you through, one of these homeworks. You know how they're set up now. You know how to, and this first one is pretty straightforward, pretty easy to get you going maybe. Make sure you see how all these things get entered. And you only have to do it once, right? There are two sets of numbers, but you only have to do one of them. So you get a second chance in case you screw up one. That's all the second one's for. So it's the best score out of the two, but you only have to do one. So if you do the first one like we did and you ace it, you're done. You don't have to do the second one unless you just enjoy it. It's so much fun. You figure, okay. All right, so that's how that works. Put that back down. This was the live load. This, by the way, gave the floor live load for larger floors, which that was not a very large floor, up over 400 square feet. There's a reduction factor because they figure you're not going to have the floor totally filled with the load. So you can work this little equation for the reduction factor. This part here, we used to call influence area. It's now just a way to calculate the influence area. Influence area means the area that, it's not the tributary area, but it's just the area that would contribute load to the member, right? Like for this, the tributary area of this floor, the tributary area of the floor on this beam that we were working would have just been half of it, right? This is the tributary area. But the influence area means anywhere I put a load, it would have an influence on that member. So I can put a load anywhere on this floor and it would influence this member. So the influence area is double that. So the KL factor there, I guess, is 2. And there's a table that KL is in, a table on the same, at chapter 4. It's got that same number, 4.7-1, I think. Is where you just look up that KL factor. Okay, So that gives a floor. Then there's also roof. There's also live loads on the roof. Live loads on the roof have nothing to do with occupancy, right? It doesn't matter who's inside, what you're doing on your inside of the building for what's going on the roof. The roof is construction loads primarily, maintenance, repair, that kind of load. And that would be influenced by a couple of things. Again, the size of the roof. If it gets very big, you're not going to have it totally loaded with people working on it. And also the steepness. I guess the steeper it gets, some of these people working on it fall off or something. At any rate, there's less, you can get less load on it as it gets steeper. So those equations, reduction equations, are given by, in this section. This is the one, there are two facts. So the base is 20. The minimum would be 20. And then you can affect it by, I'm sorry, did I say that one? The max, the maximum is 20. And then you can reduce it down to as low as 12. So it's somewhere between, when you put these factors on it, it's going to come out between 20 and 12, somewhere. So you could just use 20 and be done with it and not worry about it, and you'd be safe, right? That would be the maximum. But you can reduce it a little depending on the size. So you can see you could reduce it as much as 40% if you had an area. And this is the tributary area on that member. So this is by per member, right? That you calculate this. And then this is the slope factor. And the slope in terms of the rise, number of inches per foot. So this is inches, like it says here, inches per foot rise. So as it gets steeper, again, you could have a maximum of a 40% reduction, right? Okay, so you put those factors on, and that gives you then the roof load. All right, the next one we can look at, kind of an interesting one now. With a little bit of snow falling outside. Snow loads. Michigan is, what a wonderful example of snow loads. Look at our state. Oh my goodness, it's like a ladder. We're the fortunate ones down here. Here's Washtenaw. Okay, so we're maybe in 25, I guess. As you go north, 30, 40, 50, 60, 70. Look at this. Oh my goodness. 100 pounds per. Has anybody ever been up there? Let alone in the winter? I don't know. How could you even travel in the winter up there? It must be 100 pounds a foot. I looked this up one time. The density, of course, density of snow varies depending on, how heavy it is, but whether it's a wet snow or a light fluffy snow. But that's like, over 10 feet of snow, 12 feet of snow or something. It's a lot of snow. Anyway, so yeah, the first thing is to look at the map and figure out what your ground snow is, and then you use that ground snow to calculate first a flat roof snow load, and then if you do have a slope, you can add in or factor in the slope on it. So the flat roof snow load, initially there's a 30% reduction on the ground snow, and this is the idea that you're elevated, some of it's going to blow off, and it probably won't blow back up on it, right? So once it blows off, you've lost it. So you'll lose maybe 30% is what the estimate is there, just from it blowing off. And then there is this importance factor that we talked about earlier. Here it is for snow, all right? So depending on your category, this is what we talked about right way back at the beginning. If you're a emergency, if you're a fire station, you get 20% higher if your garage, I don't know. I tell you, when I do my garage, I'm not going to reduce it. I don't want my garage falling down like that. It's up to you. You can always make them higher. These are minimum loads, right? Minimum design loads. So you're free to, if you feel you have a little bit better judgment or reason to make it higher. Oh, I'll give you a good example. Snow loads. Oh my gosh. And I actually experienced this. I used to live down in Tennessee for a long time, and I was actually there when they had the 50-year worst snow. We had in East Tennessee, it was close to 2 feet of snow, maybe it was 1.5 feet. It was a lot of snow. We never get that much snow, and it came and it lasted like a couple of weeks, which is very unusual. Well, unfortunate part of it, one of the most unfortunate parts of it, the facility that housed all of the electrical repair vehicles, all the people that go out and fix the power lines when they fall, all those vehicles with the cranes, they were all housed at a central station, and it was outdoors, but they were covered with a shed. Well, they had rated that shed like you would. It's like a garage, right? So it would be importance category 1. Well, making it importance category 1, in a 50-year snow, it had a good chance of failing, and it did. Every single utility vehicle in East Tennessee was trapped under this shed that collapsed on them. And as a result, for the next 2 weeks, with this huge disaster of the big snow, buildings falling off, telephone lines, everybody was without power. There were no vehicles. They had to call on the power people down in Georgia, and they sent trucks up from Georgia to repair it. Oh my gosh! And this would be in hindsight, you can think, okay, yeah, it was a garage, but it wasn't just a regular garage. It was housing very critical material. So it should have been rated probably 4, not 1. But that's the way that went. And there were a lot of barns that a lot of people lost in that 50-year. So there was, people were without. Fortunately, we had a fireplace, I guess, is how we kept warm. And people came over to our house, and it was like a party for a week. But you didn't go anywhere. You couldn't move around much. Okay, anyway, so that's something to consider. I mean, you always have to have a little bit of intelligence when you make these choices on what you're considering as a classification here. Okay, exposure. Then there's some other factors. Exposure and the thermal factor. Exposure has to do with how open it is, the area, and also what kind of terrain and what kind of location it is. We'll look at that in a second. And then the temperature is the actual temperature of the surface of the roof. That will influence it. So here we go with the exposure factor. There are 3 different classes now. B, C, and D. There used to be an A, but they merged A and B together, and they just called it B. So there is no A anymore. And then from these 3 classes, which we'll look at, and they have lots of pictures of them, so they're clear what they are. It could be either fully exposed, partially, or sheltered. Fully exposed would be, the wind. It's out in the open, there are no trees around it, and the wind blows most of the snow, or some of the snow, off the roof. That would be the effect of fully exposed. Partially exposed, it's a little bit contained, so it doesn't get quite so much wind blowing on it. And sheltered means it's totally sheltered, and I think the idea is there, let's see, no, they do. They raise it, don't they? It becomes a heavier load. See, this is blowing off, so it reduces it. In sheltered, it actually gets more. And so that's, the snow not only is less likely to blow off, but I'll tell you what else it would do is if you've got something like this and these trees around it, right, and the wind is blowing like that, it's going to tend to dump more snow, I think, on the roof. So I had another friend. I'll tell you another interesting story. Hate to take up too much time. When's this class in? 10 o'clock, right? Okay, we got a little bit of time. I had a friend. I used worked in Germany for a long time, and I was there with a fellow. Worked with a fellow from Moscow. He was a Russian, and he told me this story that was, he said was a true story. That the Russians, when they built there was a big highway they built from like Moscow down to Georgian or something. It was a Trans-Siberian highway, or this big expansive road that went across empty land. Well, to make it a little bit more beautiful, but also I guess maybe protect it from the wind, when they built the road, when they built the highway, they lined it on either side with trees. So it was all the way down, lined with these beautiful trees, fir trees. And he said then, as the trees got bigger, and the wind would blow across the tundra or whatever that is, it would pick the snow up and dump it. So there was like 10 times as much snow on the road as if they didn't have those trees. If the trees weren't there, it would have all just blown off. But with the trees there, it caused even more snow to accumulate, and they eventually cut down all the trees and decided, that was a mistake. So, yeah, that is, shelter does produce more, I guess. Okay, this just shows you the categories real quickly. You can see this in the code. So, residential kind of area is slightly built up. This almost looks like our campus, doesn't it? Even in what used to be A, I think this used to be A, and now they consider that even the same kind of, there's no distinction between, how built up it is. Then C is much more open, flat, open grasslands, open terrain, okay, so it's much more open. And the specification of D is it's next to water, right? So we'd have that here in Michigan in quite a few places, and that's more likely to have a stronger wind coming off the water, I guess, off that big flat expanse. So those are your three terrains. Okay, and then the thermal factor. This just depends on how heated or not heated your roof is, and if it's kept just above freezing, then you'd have 1.1. So this would be a cold ventilated roof. So this is pretty common. A cold ventilated roof. My house would be this, right? It's normally houses are like this now. We put the insulation in the flat part, and the part that goes up above, you have vents at the side, and it vents through it. So that would be a common residential one. Unheated open air structures. Okay, so right, that would be open air. I guess this is maybe a pavilion, doesn't have walls, and somehow the totally unheated and open to the air. Okay, so that would be 1.2. If you deliberately make the roof cold, it's like a freezer building. Okay, then it's even higher, the factor. And otherwise, you'd be, if you have a slightly heated roof, not the ventilated roof, then you'd be up in 1.0. The other odd condition would be a greenhouse where you deliberately heat the roof. And this would be, like if you haven't been, now's a good time to go to what's that botanical, or Monti Botanical Garden, where they have that indoor garden over down on Dixboro or someplace. Oh, have you never been? None of you have been to that? Whoa! You should definitely just take it. If you just want to give yourself a holiday, go there one afternoon and just sit down and read a book or something. It's like going to the tropics, because you go in and it's all a greenhouse, but it's full of tropical plants. And the sun comes pouring through. Go on a sunny day, the sun's coming through, and they deliberately make all the glass single pane. And you could think, well, hey, wait, why don't you make this thermal pane? You're losing so much energy through the... Well, because they want it to heat the glass and melt any snow that gets on there. If it were thermal pane and it snowed and the snow didn't melt, it would suddenly be dark in the greenhouse, right? You wouldn't have the light coming through. So they deliberately, in a greenhouse, make it so the snow melts off, and that gives it a different value there. Yeah, but that's a beautiful place to go. Pick a snowy day and go over there. It's just like the one the tropics. Okay, and now that's all on flat roofs, so you get that flat roof value, and then you can use that to calculate the sloped roof. And the sloped roof it's the flat. This is the flat roof value, right? And this is the one factor that you multiply on there, the CS factor. So you just have to get this CS factor. And there's a table to get that from. Interestingly enough, I can't wait to see the 2022 version of the ASCE 7C if they corrected this, because they mislabeled the table as C1 instead of CT. It was supposed to be CT. It was always CT before, but somehow somebody didn't. It was a typo, I think, but it's a little bit confusing initially, maybe. But it's okay. So, and it's also a projected load. So the snow load that you calculate is like this. It's a projected load. It's not on the surface. I mean, obviously it does come onto the surface, but what you calculate is on the flat. And this is, it kind of makes sense. Snow falls like a blanket. It doesn't know what's under it. It just falls. So, and some of it, you can calculate how much slips off, I guess, with the CS factor, but ultimately it's based on that projected load. Okay, so these are the tables that you calculate CS with, and you can see there's 3 of them, depending on how warm your roof is. So this was supposed to be the CT, the thermal factor, CT, right? So this should be C. But they labeled it C1. Okay, so warm roofs, CT was 1. Then we had, remember, 1.1 was the normal. So this is the one which would be the most common, I guess, for residential, have a cold roof. And then super cold roof, okay, 1.2 or larger. They don't have one for greenhouses. I guess you on your own to figure that out. And then what you do is you just, based on the slope, right, you just read off the CS. So for very low slopes, it would be 1, as suddenly you get above 8 on 12, or here it's even higher, maybe 10 on 12 or something. Then it starts to drop off, and it drops down to this as the maximum. 0. Wow. Does it really go down to 0? Okay. So potentially, I guess if you really had a roof that's that much slope on it, whatever that comes to, nearly vertical probably. This is 45 degrees, right? So you're getting up to be pretty steep. if you're out in here, and it would reduces it quite a bit. And the two lines, because one of them is for a slippery surface, so this would be like a metal roof, tile, I suppose. The other normally you have more of a frictive surface, so asphalt, I think, would be the normal one out here. Okay, so that gives you the CS factor. You multiply it by the PF, and that would give you the load. And then you just apply it either as a balanced load, so across the entire roof, or you assume that the wind is blowing and you get a drift on one side, or it blows off of this side and accumulates onto this side. That would be this case here. Or this is with this W less than 20. If it's, I guess, greater than 20, it gets more complex. Looks a little messy, but something like that. Okay, so that, and then you can also calculate drifts. Let's see, I lost something here. Let me get this. There we go. Okay, so this is calculating drifting, and won't go into great detail, but it's like a sawtooth roof. Obviously, you have drifting between it, or if there's an obstruction on the top of the roof, you can get drifting on the windward or the leeward side. All right, and there's a table to calculate the actual dimensions of the drift, and then you can calculate the weight of it, I guess. So given all these proportions, you come into this table and you find you look for the height. You're looking for that thing there, and the other dimension. Well, okay, I guess that would be it. So you can calculate calculated drift. I won't go into detail on that, but this is what that's about. This just shows this is out my window. This is my next door neighbor, and you can see the wind was blowing in this direction and did make quite a drift right on the side of his roof. And this is no snow. You can't see it so well, but there's almost no snow on that side. It blew it all off, and it's been heavier on that side. So that is pretty much what those charts were showing you. This was a few years ago. I walked around. We had a big snow, and this is one 24 on 12, 63 degrees, and you can see they don't have much snow. It all falls off, so they don't have to deal with too much snow on that house. Some of the others, they get more drifting. You can see it drifting up in here, a little bit more on that. It's kind of hard to see, but they had some drifting. And this, I did have a student that was from Houghton. What was that, Michigan Tech up there? And he said this is his car parked in front of his apartment. Look at that. I mean, that is a bit of snow, huh? And he said people have snow rakes. They'll get out and try to pull the snow off the roof a little bit at some point in the winter, so it doesn't keep getting deeper and deeper and cause a problem. There was another. Oh shoot! I don't think I have the. See if this is actually a video, but I don't think it's. I forgot to bring the video to show you. This was as an example, was a case. I think it was actually in Massachusetts. I thought originally when I saw it, I thought it was here, but it wasn't. It was Massachusetts, and they had the people were in this building. It was in use, and they heard noises. They heard the creaking And this is the one good thing about wood. It does make quite a bit of noise. And there's always, this is true of other materials too, we usually like things to fail with a lot of warning, right? With a bit of noise, with large deflections is very helpful, so you know what's going on. And the occupants, the people that were in this building, heard the noise, and it was making enough noise that it scared them, and they went outside, and like 15 minutes later, the roof collapsed. And the people came and looked at it, and what it was that it had a drift on it. It's a little bit hard to see, but this structure was one building, and then there was something that was lower next to it, right? So it was like that, and then there was a big drift that was in this area off the side of that roof, and that overloaded these. You can see the rafters, and they just eventually lost it, collapsed. But fortunately, nobody was hurt. They were able to hear the noise and got out, so that's a good thing. Okay, let me see. We're just, this went better than I thought. Okay, so these are some of the other loads that the code talks about. Flood, which we won't get into. Tsunami is kind of specific. Rain loads, are not too common, a heavy load. Ice, potentially, and seismic. Seismic's probably one that's we could talk about a little bit, I guess. We won't use it much this semester, but it's a little bit of an interesting load. What this is showing, I mean, our area up here is pretty low seismic area. We don't have much going on. There's some sort of a fault that runs, I think it runs up like this or something. There's a earthquake zone. This is the New Madrid, and that was you've probably heard of the New Madrid earthquake back in 1812. I don't know, have you? Oh, then let me tell you, that's an interesting story. In 1812 was the last time the New Madrid fault really had a major earthquake. And now we consider it kind of dormant, and it's pretty low. We don't account for it too much in the earthquake design. However, they give these ratings or whatever, but in 1812, when it did slip, the last time it really had a slip, it was pretty horrendous. They didn't have any way to measure it. There was nothing around to measure it with. But it caused a strong enough shock wave that it caused people to stagger in Cincinnati. That they felt it walking down the street in Cincinnati. Okay, Cincinnati's way over here, right? Where's Cincinnati? Somewhere over here. So that's pretty far away. And then in Boston, wherever Boston is, where's Boston? Somewhere over here. It actually caused church bells in towers to ring. So it shifted the buildings enough, the towers, maybe they weren't too sturdy, and it caused the church, moved them enough that the bells rang in the towers in Boston. That's a long way away. So, and part of the reason why it has such a long reach is this area of the country is, the soil is it's like a big bowl of pudding. It's clay, and it's, a lot of dirt, and when you shake it, it spreads. As opposed to the West Coast, you have an earthquake on the West Coast, and it comes and it hits the Rocky Mountains or something, and it's reflected back. As soon as it hits that formation of stone that's coming up, it gets reflected back, so it doesn't really spread so far. But this one spreads a lot. And they say if we had at the time, there weren't very many. In 1812, there wasn't a lot built here. I don't know what was in Ann Arbor in 1812. Probably not very much, right? I don't know that. When did they build the university?
17, I think.
Was it? They had something? Yeah. So I guess it was. Or did the university started in Detroit though? I don't know when it started in Ann Arbor. I have to look that up. Anyway, there probably wasn't a lot, and what there was, made a little bit of it. Well, it would have been newer. Now I know, like where I live in Dexter, it's all masonry. It's all unreinforced masonry, and it's all like 150-year-old unreinforced masonry. So that you can almost, kind of chip the mortar out with your finger. Some of it's been tuck pointed and repaired, okay, but it's still probably not in the strongest condition. And if a quake like that came through, I think a lot of it would just be on the ground. And that's true through, a lot of the older Midwest little towns, right? It would destroy an incredible amount. I mean, not newer buildings maybe, but a lot of the older buildings would be, if we had that quake again, it would be a major. Anyway, and we have had little tremors lately. So I don't know, something to think about. Okay, okay, wind loads, that's what we haven't talked about yet. We could look at wind loads. I thought I was getting into seismic there, but I don't think we'll get into seismic. The wind is divided into several chapters now. It used to just be one chapter. This is where they added a lot of material. And you can, they give you a basic method to calculate wind pressure, or you can have it done, with a physical model in a wind tunnel. Like we've got here on campus, we've got a little wind tunnel, don't we? You can go see it. It's not very big, but you have to have a little bit bigger one to get a building in, I guess, is a model. But what they don't allow is what's that? The modeling, went out of my mind. The wind flow modeling. Come on, don't you guys have not done that kind of, you can't do it with a, computer modeling, I guess is what I'm trying to say. Anyway, because there's so many factors in it that it's hard to get an accurate result from that. Okay, so this is the simple Bernoulli equation, 1/2 the density times the velocity squared. That's pretty much what that equation is. This is a constant converting miles per hour into feet per second, I think, and also the density of air, which is pretty low, so that gets combined in that. They put on, here's the velocity at the other end, right? And then they have all these factors. And the factors account for how high you are off the ground, topology, wind directionality, because we assume the worst direction, and maybe it really isn't coming from the worst direction, so there's a little bit of a fudge factor there. Ground elevation, which is kind of a new one. As you go up higher, the air is less dense, so it reduces a little, that's not going to be in Michigan for sure. Okay, here are the maps. There's several different maps. You can see the main wind is on the coast from the hurricanes. We don't have, well, this is risk category 2. They give a separate map for the different risk categories, so you have to make sure you're on the right map. And we would have 107, I guess, here, miles per hour. That's not a sustained 107. I think that's only for like 10 seconds, or, 3 seconds. 3 second gust speed. Yeah, it used to be 10, and now they've reduced. It used to be 10, and it was like 90 miles an hour. Now they've reduced it to 3, and it's gone up to 107. Okay, and what do we got? And at a 33-foot height. Okay. So this is just a table that gives you the effect of height. So as you go up higher, you get this factor based on exposure that you multiply. The higher you go, that increases. These are again the exposures. Okay, we've already looked at those. Then this is a topology factor. Who was it? Frank Lloyd Wright said you should never build on the crest of the hill. You should always build on the brow of the hill. I think that was one of Frank Lloyd Wright's maxims. And because if you're up on that crest, you definitely get more wind. You can see it's a pain and a half to calculate because you got to get all these little factors in there. But then it gives you an increased factor for that being up on top of the hill there. Okay, I won't go into that. This is the directionality factor for a regular rectangular kind of building. It's 0.85. So this is saying that we assume the wind's coming straight against the wall, but in truth, it's probably not. And so there's a little bit of reduction from, like, we calculate the worst case, but it's then reduced a little bit. And things that are round, well, of course, it would come from the worst case if it were round, or almost round. So there's a change in that. Okay. Let me see. Ground elevation. Oh yeah, this is the one that they added now. The higher you go in elevation, your air density drops, right? So, okay, I guess that seems like a very kind of minor thing, but maybe if you live up in the Rocky Mountains, that would be worth calculating. Okay, so you do all that to get Q. That was what with those other calculations. This was the pressure from Bernoulli. Then you put another gust effect on it here, this gust factor, and you put a CP. And CP is the coefficient of pressure that relates the wind to the specific spot on the building. When you do a wind tunnel test, what they give you back is usually a CP. They put little pitot tubes all over the building and they measure the pressure, and they don't give you they usually don't give you, at least my experience, they didn't give us actual pressure. They just, they said you adjust it however you want. This is the factor CP for that point on the building, and then depending on what velocity you want to take for the wind, you just multiply that pressure times the CP, and you get the pressure on the building, right? Okay, and this is exterior, and this is interior. So there's a inside factor as well. The inside of the building could be either pressurized, depending how many windows you have open or something, or the HVAC system pressurizes it to extent too. Okay, this is the calculation of the gust factor, which I think I have done once in my life, and I came out, and it takes all day to do. This just shows a little bit. Each one of these factors is like a half a page calculation. It takes you an hour to do this calculation, and you end up getting 0.85. So my recommendation, it's permitted to take 0.85, and I think for what it's worth, probably easier. Maybe if you had a spreadsheet that calculated it for you, it'd be worth it, but otherwise. This is the famous CP table. This one page is an incredible lot of information on it. Gives you the CP values for the walls based on this ratio of length to width, right? And for the roof, and this is on a ratio of H over L. So here's where H is there, the mean height and L, right? So H over L, and the angle. So and each of these is a maximum and a minimum value, right, that they're giving you. These are 3 sets of values based on where you're coming there, I think. And then based on your slope. So you would take your slope and your ratio and you'd come up with some CP, right? And then you'd multiply that CP to the rest of the equation. And one time, I mean, they tell you can interpolate this way, right? And you can also interpolate that way to find values that are between these numbers. And that's interpolating. I didn't draw it right there. That's interpolating for the max and the min. So you get separate values there. And I did that when I expanded it out in an Excel sheet one time. So if you don't like to interpolate, I think I posted this on the our website somewhere. You can have the expanded version, and then you have to have, you end up. Let me see. I think do I come up with the formula at the end? Because you have also the interior. Let me see. This is for domes. Okay, and then here's the interior part. This is either, depending on whether you got your windows open, if it's fully enclosed, partially enclosed, or partially open. So this would be where the wind, you've got a window open and the wind blows in and it's pressurizing your building, right? That raises it. As opposed to if you've got the building closed and it's not so pressurized, or more of it open and it gets, I got to stop. I've gone over again. Okay, we'll stop here. That's good. I think we're all essentially to the end. You can look at the end of this PowerPoint. But, right, that calculates the different GCPIs. All right, good. Have a look at that first homework. Don't wait until the day it's due, like it's due on Saturday, right?
Yeah.
But give it a shot, at least bring it up. You saw how easy it was. See if you can at least put some numbers down and make sure that it works, that you're able to get it to work. Okay? All right, very good.